Hello everyone, this is Luke from TCE. Today we are going to learn how to calculate overall equipment effectiveness, or OEE. To understand overall equipment effectiveness, let's walk through a detailed case study based on a hypothetical production scenario. First, we need to establish the basic operational parameters. The production facility operates 240 days per year with 2 shifts each production day. Each shift lasts 8 hours, resulting in an operational total of 3,840 hours per year. We account for 0.5 hours of break time per shift, reducing the available production time to 7.5 hours per shift. Over the course of the year, this results in 240 hours of break time, leaving 3,600 available hours annually. To measure availability, we need to consider both planned and unplanned downtimes. Planned downtime includes scheduled maintenance or setup times that are known in advance. Unplanned downtime refers to unexpected interruptions such as equipment breakdowns or emergency repairs. For this case study, each shift includes 0.5 hours of planned downtime and an additional 0.5 hours of unplanned downtime. This totals 1 hour of downtime per shift, which means the runtime per shift is 6.5 hours. With 240 production days and 2 shifts per day, the total runtime per year is 3,120 hours. The availability rate is calculated by dividing the runtime per year by the available hours per year and multiplying by 100. This results in an availability rate of 86.67%. Next, we evaluate performance. Performance measures how well the equipment is used when it is running. Assuming an ideal cycle time of 60 seconds per part, the ideal production output per shift would be 390 parts. However, the actual production output per shift is 370 parts. Annually, the ideal production output is 187,200 parts, but the actual output is 177,600 parts. The net operating time per shift, after accounting for performance, is 6.17 hours. The net operating time, calculated by subtracting the time lost due to performance issues such as minor stoppages or slow cycle times from the total runtime, amounts to 2,960 hours annually. The performance rate is then determined by dividing the actual production shift output by the ideal production shift output and multiplying the result by 100. This calculation yields a performance rate of 94.87%, reflecting the impact of performance losses. For quality, we need to look at defective parts. Quality measures how well the equipment produces good products. There are 5 defective parts per shift, totaling 2,400 defective parts per year. The full productive time per shift, after accounting for these defects, is 6.08 hours. This annualizes to 2,920 full productive hours. The quality rate is calculated by dividing the full productive time per year by the net operating time per year and multiplying by 100, giving us a quality rate of 98.65%. Finally, we calculate the overall equipment effectiveness. This is done by multiplying the availability rate, performance rate, and quality rate. The OEE is computed as 0.8667 for availability, 0.9487 for performance, and 0.9865 for quality. Multiplying these together results in an overall equipment effectiveness of 81.11%. This percentage reflects the combined effectiveness of equipment performance in terms of availability, performance, and quality. Next, we are going to look at a simplified calculation for overall equipment effectiveness. In this approach, we combine availability and performance into a single factor called effective utilization rate. To start with the operational overview, the production facility operates 240 days per year, with 2 shifts per day, each lasting 8 hours. This totals 3,840 operational hours per year. With 0.5 hours of break time per shift, the available production time per shift is 7.5 hours. Over the entire year, this results in 240 hours of break time, leaving us with 3,600 available hours annually. Now, let's incorporate the effective utilization rate. We set this rate at 86%. This combines the impacts of both availability and performance. The downtime per shift, which includes both planned and unplanned downtimes, is 1.05 hours. Consequently, the net operating time per shift is 6.45 hours. Annually, this results in a total net operating time of 3,096 hours. The effective utilization rate of 86% reflects the proportion of net operating time that the equipment is effectively used. For quality, we measure the scrap rate, which represents the percentage of defective products. Here, the scrap rate is 1%, indicating a quality rate of 99%. This means that 99% of the products produced are defect-free. The full productive time per shift, taking into account quality, is 6.39 hours, leading to a total full productive time of 3,065.04 hours per year. Finally, we calculate the overall equipment effectiveness. To determine OEE, we multiply the effective utilization rate by the quality rate. With an effective utilization rate of 86% and a quality rate of 99%, the OEE is calculated to be 85.14%. This simplified calculation demonstrates how setting the effective utilization rate at 86% helps streamline the evaluation of equipment effectiveness. By combining availability and performance into one factor and accounting for quality, we obtain a clear and concise measure of how effectively the equipment is being used in production. We will now continue with an extended OEE calculation. In this calculation, we will incorporate downtime for each of the main OEE sections to provide a more detailed and accurate assessment of the production operations efficiency. Let's start with the operational overview. The production facility operates for 240 days each year, with 2 shifts per day, and each shift lasts for 8 hours. This setup results in a total of 3,840 operational hours annually. Each shift provides 8 hours or 480 minutes of scheduled production time. However, accounting for breaks, which are 30 minutes per shift, reduces the effective production time to 450 minutes per shift. This translates to 7.5 hours of productive time per shift. Consequently, the total annual available hours, after accounting for breaks, is 3,600 hours. Now, let's dive into the availability aspect in more detail. The planned downtime per shift consists of several components. Setup and changeover downtime, which involves preparing the equipment for a new production run, accounts for 20 minutes per shift. Scheduled maintenance downtime, necessary for routine upkeep of the machinery, takes 15 minutes per shift. Cleaning and sanitation downtime, required to ensure equipment cleanliness and adherence to safety standards, adds another 5 minutes per shift. Lastly, quality checks downtime, which involves inspecting and ensuring product quality, also takes 5 minutes per shift. Adding these together, the total planned downtime per shift is 45 minutes. In addition to planned downtime, there's unplanned downtime that affects availability. Equipment failure downtime, due to unexpected breakdowns or malfunctions, contributes 5 minutes per shift. Material shortage downtime, which occurs when there is a lack of necessary materials, also adds 5 minutes per shift. Combining these, the total unplanned downtime per shift is 10 minutes. Thus, the overall total availability downtime per shift, which is the sum of planned and unplanned downtimes, amounts to 55 minutes. This leaves a runtime of 395 minutes per shift, which is equivalent to about 6.58 hours. Over the course of a year, this results in 3,160 run hours, giving an availability rate of 87.78%. Turning to performance, the analysis looks at downtime due to various factors. Minor stops or micro-stoppages, which are brief interruptions in production, account for 10 minutes of downtime per shift. Speed loss downtime, which results from reductions in production speed, adds another 5 minutes per shift. In addition to these cycle time losses, there is production rate loss due to minor adjustments, which takes 5 minutes per shift. Therefore, the total performance downtime per shift is 20 minutes. After accounting for this downtime, the net operating time per shift is 375 minutes, or 6.25 hours. Annually, this equates to 3,000 net operating hours, resulting in a performance rate of 94.94%. The effective utilization rate is a measure that combines the impacts of both availability and performance. In this case, it reflects how well the available production time is utilized after accounting for both planned and unplanned downtime, as well as performance losses. This rate stands at 83.33%. It represents the efficiency with which the available production time is used, considering both the time lost due to availability issues and the time lost due to performance inefficiencies. Finally, for quality considerations, defect-related downtime includes time lost due to scrap and defective parts, which takes 5 minutes per shift, and rework, which adds 2 minutes per shift. The total quality downtime per shift, therefore, is 7 minutes. Consequently, the full productive time per shift, after accounting for these quality issues, is 368 minutes, or 6.13 hours. This results in a total of 2,944 full productive hours per year, leading to a quality rate of 98.13%. Combining all these factors, availability, performance, and quality, the overall equipment effectiveness, or OEE, is calculated to be 81.78%. This percentage reflects the combined impact of these three areas on the overall efficiency and effectiveness of the production process. In conclusion, calculating overall equipment effectiveness is a powerful way to assess and improve the efficiency of your production process. By breaking down OEE into its three core components, you can pinpoint exactly where losses are occurring and focus your efforts on targeted improvements. Thank you for your attention and see you at the next session.